And this meeting is being recorded. Nice job. You want to catch this? Catch this for posterity? Oh crap, that means I have to do a good job. All right, well, so Sarah came to Berkeley at the start of a multiple confluence of different trends in the research group. We started diving into aspects of feedback systems, trying to understand how to merge machine learning with control. And we were interested in this for multiple reasons. One, at this time, everybody was really excited about self-driving cars before we knew better. And we really wanted to understand if it was going to be possible to make them safe and robust and reliable and not get people hurt. And at the same time, I think we've started to really realize that a lot of our machine learning systems that we've been deploying out in the world had some negative consequences when just thrown into a mix with people. And Sarah was interested in both of these aspects and really has built an amazing research portfolio, kind of showing how you can have a very just expansive multidisciplinary PhD that covers all sorts of different topics, all sorts of different interests, problems that really connect to real world issues, and yet ground it in some serious fundamental theoretical underpinnings. So it's been a pleasure to be Sarah's advisor. I'm really excited to see this synthesis and this talk. And without further ado, Sarah Dean.
All right, thank you, Ben. So yeah, today I'll talk about my work that I guess appears in my dissertation, reliable machine learning in feedback systems. That's sort of the overarching theme. So to start us off, the reason I guess that I've done work in this area is because machine learning is really a promising tool for processing complex information. Many of us interact with systems powered by machine learning in our daily lives, whether it's a speech assistant, whether it is systems for categorizing the objects and images, or whether it's machine translation. There have been real benefits to using machine learning in these cases. And these successes have led us to also question whether we can use machine learning to not just process the information, but actually to act on it. And there's also a lot of success in this area that have made people excited, whether it's in kind of a closed environment of gameplay, as in the game of Go, where AlphaGo can beat the performance of human experts, or even in kind of physical domains that are difficult, like manipulation, where physics are hard to model. But ultimately, machine learning is still an unreliable tool when it's used in this way. And we've seen this in high-profile failures of self-driving cars, whether it's a Tesla on autopilot mode that crashed into a barrier on the 101 when it failed to detect that it wasn't in the exit lane, or the first sort of pedestrian fatality as a result of an Uber car in self-driving mode, which failed to detect or even slow down when there was a pedestrian kind of with a bicycle crossing the street outside of a crosswalk. But it's not just physical accidents that occur. We also sort of have these massive social media systems that don't just process complex information, but make choices about what to show us. And these have been implicated in things like radicalization on the internet. So what do I mean when I say machine learning? At the center of machine learning technologies is something called a model. And this is usually constructed from a bunch of training data. A model is something which takes in observations and makes a prediction. So for example, if you're driving a car on an icy road, you might want a data-driven model to help you predict the future velocity of the car based on its current velocity, steering angle, and acceleration. Or maybe instead, you have a dash camera on the car. And what you'd really like is a model that can take in the camera image and tell you where in the world you are. And in other domains, we also have human behaviors that can be predicted by models. So based on the way that somebody has historically rated movies, can we predict how they'll like the new movie? And all of these examples, the observations and the training data come from some world, some environment. And when the model makes predictions, we don't just look at them and say, okay, that's cool. We use those predictions often in some kind of policy. And the action that we take often affects the very world that our observations came from. This creates a feedback loop. And there are sort of dangers of using static predictions made by machine learning models in a dynamic world. We see this in catastrophic failures like car accidents, the propagation of inequality and bias in our historical data towards the future, or in the creation of systems that end up promoting addiction to them. But at the same time, there are promises of data-driven solutions. And in fact, if we use our observations about the world, about the data we collect, If we use it well, we could design systems that guarantee safety in a wide variety of conditions, or systems which promote equity or promote discovery. So how do we do this? In my PhD work, I've thought about an approach that is both data-driven and robust, which centers on the question, where could the system go? What will happen to the world as we deploy this policy and take these actions? So I want to ensure reliable outcomes by making sure the system goes where we want it to go, by encoding different values through a lens of reachability. So where will the system reach? I do this by bringing tools from machine learning, which allows us to think about data and to quantify the uncertainty we have that remains despite the data we've observed. Control, which allows us to kind of describe what we want through some type of robust reachability condition and make it robust to those uncertainties that remain. And finally, optimization, where we optimized over this condition to actually design the policy that will work. So what do I mean when I say reasoning about reachability? Well, where the system goes, which is the system's trajectory, I'll say, depends on how the system changes over time. Those are the system dynamics. Where the system starts out, where the system is, that's the system state, and which actions you choose by the policy or the controller. So this is a counterfactual question. Depending on what actions I choose, the system will behave differently. And there's also uncertainty in a lot of these systems. That's the whole point of using data, which means that we may not know exactly how the system changes because perhaps we don't have a good physics model of tires on ice. We also might not know where the system is. Perhaps we can't perfectly observe the state with perfect sensors. And of course, these uncertainty sets that result will change depending on the actions chosen by the policy or by the controller. And so this problem can become hard when we think about long time horizons. But yet, if we kind of do it the right way and in certain settings, we can articulate when we can expect to ensure reliable outcomes. And I want to talk about two different types of outcomes that we'd want. One is safety and the other is discovery. Safety is kind of an anti-reachability criteria. It says we don't want to go everywhere. We want to ensure the system stays within a particular set. So the system must remain in the safe region. Discovery, on the other hand, is sort of a different desire. We want the system to actually reach many different regions. And I'll explain why we might want these things in the context of some examples. In particular, I'll focus on 3 different projects. The first is safety with unknown dynamics. So we don't know how the system changes, but we still want to ensure safety. The second is safety with complex observations. So the way we observe the system state is complicated, like through a camera, but we still want to maintain safety. These are kind of both motivated by physical concerns. And finally, I want to talk a little bit about recommendation systems, which are indeed also dynamic feedback loops, but kind of require a different lens to kind of articulate what we would like them to do. So let's start with safety with unknown dynamics. So here we have, I'm just showing a video of something that I worked on during my PhD, although it didn't quite make it into my thesis, is this car that races around a track autonomously based on experience. So it's data-driven, it's performance optimizing, but crucially it's also safe. It's not hitting into the wall. It's actually in this very room. And that raises the question, how much data do you have to collect from a system to safely control it? When do you know that you've done enough? So to answer this question formally, I'm going to frame it in terms of an optimal control problem. This is also essentially the same framing as a reinforcement learning problem, where we can model a task in this language. So let's say we want a car to quickly move to some goal point. We'd like to design a policy, pi, that minimizes the cost of doing so. And the cost specifically usually depends on the system's trajectory. And I'll write down the system's trajectory in terms of the state, x, and the action or the input, u. So both of these things sort of affect how costly it was to take this, to do this task. And the trajectory is determined by that policy that we're choosing, this policy that determines our inputs, as well as the system's dynamics, which determine how our actions change what the system does. And so this interconnection gives rise to the trajectory. Finally, we also want to keep the system safe. It's no good to drive the car super fast if we crash at the end of it. And so we can also add safety constraints to this problem. I'm also going to study this problem in the presence of disturbances, which are sort of irreducible uncertainties about the world. So perhaps, a bumpy road that we can't ever quite expect to model. And we usually want to kind of minimize a cost that takes into account either the expected behavior under disturbances or the worst case. And if we kind of knew all the parts of the problem, and if it was simple enough, there are a lot of methods that allow us to design an optimal policy pi star that kind of achieves this minimum cost. That's the best we could do. But in this kind of project, I want to focus on the case that we don't know the dynamics. So since we don't know the dynamics, it's unclear how to design that optimal policy. And to kind of answer that question I asked in the beginning about how much data we need, I'll pose a sample complexity problem, a sample complexity question. So how much data do you need to collect from a system to safely control it? We have our unknown dynamics, but we can choose inputs for the system and we can see the outputs that occur. And using this data, we can, through some procedure, design a controller a policy or a controller, which I'll call pi hat. And then there's kind of two goals about whatever the design procedure is. The first one is to guarantee safety, so ensure that pi hat keeps the system safe. And the second one is also to achieve good performance. And we measure performance by suboptimality, which is the cost of the data-driven policy pi hat compared to the cost of the true optimal policy pi star that we would have designed if we had known the system ahead of time. So just to kind of motivate this, I'll show you a simple numerical example of a procedure that kind of achieves these goals. I'm going to consider a system that follows double integrator dynamics. Double integrator is really just Newton's second law, F equals ma. And so it says that if we apply forces to a system, those forces are the acceleration, essentially, which affect the velocity of the system, which in turn affects its position. And so the state here will be velocity and position. Let's say our goal is to kind of regulate the system around some point. So this might be kind of following a center line in lanes, but we also might have some constraints. So not to veer too far to either side of the center line and not to go too fast or too slow. Now, I told you the system was a double integrator, but let's say we didn't actually know that ahead of time. What could we do? We could first collect data. So here I'm just plotting some inputs. So these are forces that we're kind of pushing the system, pushing and pulling the system a little bit to see what happens. We can then try to estimate those dynamics, the model of the dynamics, which predicts the next state on the basis of the inputs and the previous state. And over time, those estimation errors will go down, which we can check because this is a numerical example where we know the true system. And then finally, we can design controllers that sort of are robust to the remaining estimation errors, but still keep the system safe. So I keep it within this box. And starting from many different initial conditions, so many different positions and velocities, I can still drive the system and regulate it to the center there without ever going unsafe. So that's kind of an example of how this could work in practice. So how do we actually kind of show that this works formally? I'll study this in the setting of the linear quadratic regulator, which is an optimal control problem that's very classically studied. It has linear dynamics, as you might expect. We'll assume that those are unknown. The dynamics are parameterized by two matrices, A and B, and those are unknown matrices. The cost of the system is quadratic, where Q and R are sort of specified matrices that describe the relative importance of keeping the state small compared to the inputs U. And finally, we also want to keep the system safe, and we'll do that with linear constraints, where this sort of describes perhaps a polytopic region, maybe a box, like I showed in the previous example, that just describes what safety means in this setting. And our goal here is to design a linear controller from data. And because everything is linear, I'm now switching from the notation of pi for a generic policy to k for a linear policy. And we'll call that policy that we're trying to design k hat. So the framework that we'll use is sort of what we went through in the example. It's safe data-driven control in 3 steps. The first step is to collect data. For this, we run the system for t time steps while choosing safe excitations. And I'll get more into each of these steps in the following slides. The second step is to fit a model and then characterize its errors. Because we're in a linear setting, we can use least squares estimation to use data to estimate some A hat and B hat. And then crucially to also estimate how wrong we might be. So epsilon A and epsilon B are the errors in those estimations. And finally, we can synthesize that data-driven controller using the estimates, not just the estimate of the model, but also the estimate of our errors in the model to ensure that the system will be safe regardless of some imperfections. So the result that I'm now going to sort of walk through is basically showing that this works, that under certain conditions, we can believe this procedure will work. And it says that as long as you've collected enough data, then you have a high probability guarantee that the suboptimality, so this difference between the cost of the data-driven controller and the true optimal controller, is kind of bounded by the following few quantities. And I'll point out kind of what's salient about them. This first one is sort of an inverse signal to noise ratio term that compares the size of the noise, which is inherent to how the system kind of rolls out, that you have no control over, that's the disturbances, to the size of the excitations that you're able to inject. The second term is sort of a sample complexity term. It tells us that as we get more data, so we have T data points, this term will decrease as the dimension over T, where dimension just describes the dimension of the state plus the input. So it's about how many things we're estimating. And also we see here the kind of high probability dependence where delta is sort of the probability that we actually didn't quite get what we wanted. And there's a logarithmic dependence on it, which means that delta can become exponentially small as we allow T to increase as we collect more data. And lastly, there's a sensitivity term, which is about the behavior of the system under the true optimal controller. And that kind of comes out of control theoretic quantities. So this result is something that was one of the first projects I worked on as a PhD student in the case of unconstrained control. So where we don't actually care about safety specifically, we just care about bounded cost, which implies stability. And so this was sort of the first general sample complexity bound for this problem. Now, LQR, the linear quadratic regulator, the setting is very classical. If you take sort of any graduate class on control theory, especially optimal control, you'll probably know it well. And so it had been studied before. Previous work kind of classically considered the problem asymptotically, showing that as you get infinite amounts of data, then you infinitely estimate correctly, and therefore you can just think about LQR in the case that you know the model. In 1997, there was some work that approached this problem from the perspective of PAC learning, or probably approximately correct learning, which is roughly the same as the perspective we take here. But the work suffered from many strong stability and contractivity assumptions that are hard to verify in practice. And then in 2011, Abbasi Yakadori and Shepasavari also studied a sort of adaptive method for this problem. It was very foundational work, but the method they proposed was computationally intractable, and they also make a very strong stability assumption. The benefit of the framework that I'm talking about now is that it's flexible, and so it allows us to analyze also the constrained problem so that we have linear safety constraints on the state and some initial course estimates. We can still kind of make this style of sample complexity guarantee. And so I'll kind of walk through how we got there. There's three main ingredients. The first is a statistical learning rate, which says how fast we can learn about the system from the data we collect. The second is a method for actually designing these controllers K that are robust to uncertainties and ensure that the constraints are satisfied. And then finally, we have a suboptimality analysis on the constraints themselves, or on the synthesized controller that we have, to say, based on our errors, how much worse are we doing than we could have? So the first step is to collect data from the system with a safe excitation. And what I mean by that is just the combination, so choosing U, the control inputs, to be the combination of a linear feedback controller, that's this first term, plus kind of a probing excitation. And I'll talk a little bit more about how you might design that linear controller, but for now the point is we just have this kind of additive combination of something that keeps the system safe as well as excites it, so that we can sort of see its behaviors in all directions. From this data, in the second step, we do least squares estimation. And this is a relatively straightforward approach where we minimize the squared error on the data that we've seen to estimate A hat and B hat. And now remember that the system is also driven by disturbances. And so this won't be kind of an exact procedure. Some errors will remain. But as long as we kind of choose our excitations carefully, and as long as the disturbances or the process noise is independent over time, it's relatively benign, and we can still characterize our errors. So as long as the controller we use is stabilizing, then after long enough, we can bound the errors in the estimates, delta A and delta B, by this term that should look somewhat familiar. So we see the inverse signal to noise ratio term, as well as the sample complexity term. And that tells us how our errors decrease, and we saw already that that entered into our ultimate suboptimality bound. So there's just one step that remains, which is actually to design this controller. This controller that we're designing has to keep the system safe, even though we have this process noise and excitation that we're injecting, as well as the uncertainty in the dynamics that we don't actually know. So I'll very briefly give a high-level overview of the framework that we use to make these guarantees. The optimal control problems, when you want to design the policy, are non-convex in the linear controller. And visually, it's because of this cycle that happens. That kind of feedback loop is difficult to reason about analytically. And so we kind of turn to an alternate parameterization called system level synthesis, or SLS, which really just makes the system, instead of looking like this loop, look like a line. So we have this map going from the disturbance W, so this is the injected noise, directly to the states and inputs. And I use the variable phi to represent this map. I'll call it the system response variables. There's a relationship between the map phi and the controller and the dynamics that you design. So SLS actually shows there's an equivalence, which means that we can work in one space and translate it to the other space. And for our purposes, working in system response space will be much easier. Now, it's especially important when we move to robust control, which is where we handle the fact that there are uncertainties in the dynamics that we have. Of course, robust control is something that has been considered since, I don't know, late 70s, 80s, and 90s, has been sort of a huge field with a lot of success. However, at least we don't know of any way to kind of analytically characterize how the size of the uncertainties that you design with affect your degradation in performance in sort of a data independent way. And that's something that SLS allows us to do. The reason that it allows us to do this, so recalling kind of thinking about our linear feedback controller, we have this loop, and then now we have this delta A and delta B, which are kind of our uncertainties, our errors in the matrices. So we don't know what delta A and delta B are, but we do know how big they are. Thinking about it in kind of this picture here ends up being very difficult. But when we kind of translate into the system level synthesis setting, we can isolate those uncertainties kind of into this delta block, and then analytically write down how the uncertainty affects the system trajectory. So we have our design system responses, which depend on our estimates, A hat and B hat. And then we also have this term delta, which depends on our errors. And then of course we have the process noise as before. And this is kind of a nice expression that we can work with. We don't know what delta is, but being clever, or actually not super clever, using things like triangle inequality, we can bound its effect and formulate a robust control problem. And that gives us a way to design a controller through robust system level synthesis in terms of our estimates A hat and B hat, and the size of the errors, epsilon A and epsilon B. So even though we don't know delta A and delta B, we do know epsilon A and epsilon B. And the real benefit of SLS is not just the procedure, it's also the fact that we can show the following result. As long as the robust problem is feasible, the controller that results from it will keep the system safe. And as soon as the errors are small enough, we can even guarantee bounded suboptimality. So this is comparing the cost of our data-driven controller to the true optimal controller. And it's bounded in terms of the size of the errors, epsilon A and epsilon B, and the system response of the true optimal controller. So sort of the system level synthesis framework allows us to write down this quantity. And that actually brings together everything that we needed to show this result, where the statistical learning rate showed us the first two terms in this bound. The method for kind of synthesizing a robust constraint-satisfying controller allows us to guarantee safety. And the suboptimality analysis gives us this last term in the bound. So in kind of, just to summarize what we've gone through since that was a long section, data-driven controller design, the method that we propose, ensures safety and optimizes performance, learns the unknown linear dynamics, and has finite sample guarantees. This method also extends into an adaptive setting where you repeat the 3 steps that we went through over and over again to continuously kind of refine your estimates. And it kind of extends in a straightforward manner. But now I want to move on to kind of our second setting, which is where the uncertainty stems from the observations about the state rather than the dynamics themselves. So this is also kind of motivated by our example of this racing car. It's motivated by the fact that the only position sensor on board the car is actually a dashboard camera. And we use open source computer vision methods to kind of localize key points within a frame and then determine the actual position of the car at each time step. That goes into a more complicated control loop that's not fully captured by the linear controller stuff that I've been talking about. But the kind of crucial thing that I think is interesting to study is how do you actually remain safe in a system like this when you have imperfect perception and imperfect measurements? So that brings us to the problem setting of perception-based control. I'm going to suppose known linear dynamics. So as before, the way the system evolves is described by this linear equation, and this time we know what the equation is. The kind of the catch or the hard part will be that the observations about the state, x, are through this complicated function. So instead of just seeing the state and designing a controller that is a state feedback controller, we have to design a controller that acts on these complicated observations, which is generated by some appearance map I'll call Q. That's a function of C times the state. So C is a matrix that kind of determines which parts of the state affect the observations. So just as an example, I have that car racing around this room. The observation that appears is an image. And so the appearance map takes this car state, which might include things like its velocity, its position, and output something like just its position. And then that position will generate an image. In the example I showed, we had this kind of computer vision-based perception map that then took the image and estimated where the car was. Now, there might be some mismatch, perhaps where the car actually is and where we think the car is not quite the same. So we can also write down that this perception map is really just giving us this measurement of the state, C times X, plus some errors. So this looks a little bit like a classic model of measurement noise. And we can think of it this way. Our perception map acts on these complicated observations to give us a virtual sensor, a virtual linear sensor with some type of error. Now, this, putting together the linear dynamics and our new kind of sensor model, we have something that looks a lot like linear control. A little bit different from the example that we went through before because now I have output sensors instead of just state observation, but it's something that's very kind of easy to classically handle. And in fact, actually, this perspective is sufficient to design controllers if you can characterize the errors. But I want to talk today about kind of a setting where we can characterize the degradation due to uncertainty. And so I want to compare this to the setting that we have a perfect perception map, P star. Well, we don't have it, but it exists. And if it existed, then our virtual sensor would have no errors. And the linear controller that arises from that setting is going to be called K. And then our optimal, our full optimal policy pi star would be combining the linear controller K with that perfect perception map. So, as if we had a camera and we had a perfect way to look at a camera image and say, okay, this is your position in the world. But of course we don't. We only have our normal perception map, P, and the combination of the linear controller K with P we'll call our certainty equivalent controller. So in this case, we're using P, which may be data-driven. In any case, it's not quite as good as our optimal controller. So I'm bringing back system diagrams again, and I'm doing it because I want to motivate the use of system-level synthesis Once I have a system, even if it's an output feedback system, where outputs Y are being fed into a linear feedback controller to determine inputs, I can really just think of the system in terms of the process noise and those errors E. And I can write it down just like we did in the previous section in terms of its system response. So now the system response is determined by A, B, and C, the matrices, the dynamics and measurement matrices, and the controller K. But I can represent it this way, there's an equivalence, as this transfer function phi. And if I want to kind of get specific about it, I can kind of distinguish the parts of it that are mapping the process noise W versus the measurement error E to the state and to the input. And so I've written it that way. This kind of perspective immediately allows us to argue that we can bound the suboptimality as long as those errors E are bounded, so our perception errors. And we can bound it in terms of the norm of the system response and the norm of the errors. So how do we bound the errors? There's a few different ways, and I've done projects that look at it from different perspectives. I want to talk today about a more statistical perspective, which says, well, just throw a lot of data at it, learn some kind of deep network through function approximation. Shouldn't that be able to work? Shouldn't we be able to just learn a perception map that way? And so I'm going to study a slightly simplified version of doing that, but it's still a non-parametric regression problem. So unlike in the previous project where we were estimating A and B, those are parameters of the system, we're just trying to get some map that gives us good predictions. And in particular, the predictions sort of are generated from data as follows. If we have a bunch of dots, those are all data points that kind of tell us for a given observation Z that we observed, this was the corresponding kind of state or position. Then around each data point, we sort of have this bump of support saying that, well, each data point should tell us a little bit about the data points next, about the behavior of the system next to it. And then we kind of add up over all of our data points and we get some prediction. So for any new image that we see, we can now make a prediction about the position. This is, of course, not exactly how deep neural networks or other things that are popular in machine learning work, but it is sort of a good first order approximation to think about their behavior. If we further assume that the system will always operate within a bounded region and we can kind of characterize the region of operation, and we assume that the true perception map P star and the appearance map are continuous, so that the way images are kind of generated relative to position is kind of a continuous map, then we can show that that certainty equivalent controller, pi hat that I described, using our data-driven perception map, compared to the true optimal controller, pi star, again, has a bounded suboptimality. Although this time it looks a little bit different than what we saw before. So let me highlight kind of the things that matter. One of them is this bounded radius of operation. So how large of an area does my map need to be good for? The second one is kind of the continuity of the perception and appearance maps. So sort of how abruptly will images change as I move a little bit. Here we kind of have a noise term divided by the amount of data points. So sigma to the 4th power over t. So as t gets larger, the amount of data we collect gets larger. Again, this decreases. But it decreases a little bit different now. We have these kind of exponential dimension terms. Here, this is the dimension of kind of the measurement subspace. So in the example of position, it might just be xy, so that's dimension 2. It might be xy angle, that would be dimension 3. But this dimension has an exponential dependence here. So if I want my errors to be arbitrarily small, the amount of data I need, t, needs to scale as something to the dimension power. So this bound is maybe valid for kind of simple robotic systems operating in low dimensional spaces, but as the dimension increases, this bound increases quite rapidly. And this is different from from part of the work I showed before on parametric estimation, because we had sort of a smaller number of parameters to estimate. This sort of has to do with uniformly covering the space that we've observed in. And this is actually inherent to trying to bound errors point-wise. It's inherent to uniform convergence analyses. It sort of shows that asking for feedback control guarantees is much stronger than what we traditionally study in machine learning. Finally, I just want to point out this last term, which appeared as well on the previous slide. This is our control theoretic term, and it has to do with how the optimal linear controller is sensitive to measurements. So the more sensitive to measurements it is in the optimal case, the more data you'll need to have a small error. So that kind of brings me to the end of the setting where we've kind of compared two different ways that uncertainty might arise in systems and that we might try to use data to mitigate it. And I now want to switch over to a sort of different thrust of my work, which focuses less on systems that are described by linear dynamics, which are maybe okay approximations of physical systems, and more on systems that are described by dynamics that involve people and populations. So before I get into recommendation systems, I just want to motivate how feedback arises here. Imagine we have an individual applying for a bank loan. Their financial status will be used by the institution to make a lending decision, but inevitably that lending decision affects their financial status moving forward. Similarly, an individual applying to an academic institution will send their academic history. Some administrator will make an admission decision, and then whether or not they've been admitted will inevitably affect their academic history moving forward. And so we have these loops. Now, in an increasingly data-driven world, these institutions might use data to create models to predict success of repayment or success at, GPA or graduation, and use these models to actually influence their decisions. How do we make sure that we're not just kind of propagating historic bias in these cases? Well, one sort of popular method that's, I guess at this point, I would say it's pretty popular within the machine learning community, is to think about fairness, where fairness is not exclusively, but often defined in terms of equality criteria on decisions between groups. So thinking about different demographic groups of individuals and ensuring that different statistics like acceptance rate or true positive rate are equal among them. In some work that I've done during my PhD, we've tried to shift the focus a little bit one step down this feedback loop to think about not the decision itself, but the impact that decision has. In particular, we looked at a kind of simple model of impact to ask what the impact of fairness constraints are in a decision. Do they promote well-being? And we sort of answered in the negative that in general, for any general settings, you can't guarantee that just fairness will ensure good outcomes. And that kind of inspired us to look a little bit more rigorously on what it would mean to try to incorporate a measure of well-being, welfare, or outcomes to a decision process, even when that's kind of a noisy measurement. I'm not going to talk about either of these in detail, but I do want to highlight that both of these kind of papers think about just a two-step mechanism from, in the example of lending, financial status through a decision process, and the decision process having some impact model on the future financial status. Now, of course, you can try to link the two ends together into a loop and think about the full feedback loop happening over multiple time steps. But there's a few reasons that this perspective is not something that I ultimately found fruitful yet anyway. And the reason is that compared to physical systems and physical dynamics, social outcomes have limited predictability. It's much easier to predict where a car is going to drive as a function of the forces on it than the life outcome of an individual. And there's also difficulties of measurement. A lot of our models in control think about zero mean Gaussian noise, which is fair for a lot of physical sensors, but not sure if you can measure people in the same way. Furthermore, kind of the objectives, what we would like to achieve in social settings, this can be of indeterminate value or contested value. What do we really want when it comes to lending? Do we want lending to optimize the credit scores of a population? I think ultimately, the setting of optimal control looks to design a policy, but optimizing a policy acting on populations of individuals is ultimately a form of social control. And now maybe for trusted institutions that have other accountability mechanisms, this is something that exactly we want. However, in other scenarios, if the institution is a for-profit company with its own motives, I'm not so sure that that's what I'd like to do. So with that perspective in mind, I want to think about recommendation systems. In a recommender system, based on the content that I've previously viewed or consumed, like videos of animals here, the system will serve up a recommendation of what I should watch next. So in this example, I've watched a lot of animal videos and mostly cat videos. And so maybe it's not surprising that I have a cat video coming next. But what if I had gone back and changed the way I reacted? Could I have had the system give me a dog or a rodent, a guinea pig? The question I'm really asking here is, does the system enable discovery? So what I just kind of walked through is this idea that there's many paths that could be taken. For one set of ratings, I get a cat. For another set, I get a dog. For another set, I get a guinea pig. I didn't show an example where I found an iguana. Maybe it's actually impossible for me to find one because I have no videos that are kind of relevant there. It's not clear that even I could reach these 3 different types of videos. Maybe actually in the system, regardless of what I did, I would have only ever seen that cat video. How do we start to quantify this ability of individuals to control what they discover? So in some recent work, I've started to propose a way to measure this idea, to measure the amount of discovery through a notion of reachability. We define that an individual can discover an item if they can take an action so that item is recommended. So what I'm thinking of is really just this pipeline where users take actions. The action will update a preference model trained on historical data. That's a model that kind of predicts what it thinks you'll like. It's fed into a selection rule, which looks over a bunch of available items for recommendation, sorts them in some way, and then gives out a recommendation. So this is sort of a controllability condition. Can users, by modifying their actions, control what comes out at the other end? It's also a reachability condition. Can users sort of reach different parts of the preference model space in order to represent their preferences differently? Now, I've sort of shown that in settings that are kind of relevant to modern recommendation practice, this is something that you can compute efficiently enough to audit models. And so I'll briefly describe the results of an audit on the Movie Lens dataset, which is a rating history of users on movies. And I'll use this dataset to both populate the historical data and determine available movies. So any movie that a user has not yet rated will be considered available. I used a matrix factorization preference model, which is roughly almost state of the art, and a top 1 selection rule that just picks out the highest prediction. And we look at kind of the population of users here, and I'm gonna kind of specifically ask 2 questions. Does the system provide discovery to users who have just joined it and not rated very many movies yet? And what about older users who have been using the system for a long time? Second, I want to ask, do any properties of the learned preference model, so in this case, the matrix factorization model, do they affect the amount of discovery? So in order to quantify this, I'm going to plot sort of the percent of unseen movies that are reachable. So movies that have not yet been rated, how many could you reach through this pipeline? Over different model complexities. So this is just sort of a parameter of the machine learning model. Just starting with kind of a low dimensional model, I'm going to compare what the percent reachable is for users with a history of under 20 movies, they've only rated less than 20 movies, or over 200 movies. And looking at this, we immediately see a large difference where users that are kind of new to the system have a lot more discovery available. Depending on how they choose to act, they can really influence what the system will show them. Whereas users with longer histories have much less. And if we kind of consider larger model complexities, we see that there might still be a difference between the 2, but overall there's just much less discovery available. So even though more complex models are supposed to be better at prediction, they're not necessarily better at providing reachability or discovery. And even beyond kind of those conclusions, I just want to highlight that this study is not saying users won't be represented many movies, won't be recommended many movies. It's saying that even if they start to act strategically, they couldn't be recommended. So it's impossible for an individual to see more than sort of this limited number of movies. Here, the percent reachable I have sort of 10% in the best case. It's also impossible, this plot doesn't quite show it, but some movies to be recommended to any user at all, meaning that even though they are supposedly sort of in this recommendation system and available to be recommended, they're actually not going to be recommended even if a user was behaving strategically. So to kind of bring this to a close in the last 5 minutes, I'll just review that today we talked about kind of my work thinking about both safety and discovery. And we started with some projects on linear control and linear perception-based control. But this is really part of a broader thrust that I've done on topics including nonlinear control and computational imaging. And on the side of discovery, I focus mostly today on my work on recommender systems, but I also mentioned how I've thought about automated decisions in sort of a similar manner. This is part of a broader thrust of work as well, which has really been supported by some interdisciplinary projects that I've thought about with graduate students in a group that I founded called GEES, Graduates for Engaged and Extended Scholarship in Computing and Engineering, which has helped me to think about the place of technical research in the broader social context and how to articulate what the limits are. So just to kind of briefly talk about what I'm doing next, on the side of ensuring safety and data-driven control, I think there's a wide range of problems to attack, both thinking about complex observations and trying to improve that exponential dependence when there is more structure in the setting, and also for systems that are just fully nonlinear. Really, I think there's a spectrum between the classic engineering and robotics method, which is using things like visual inertial odometry and planning that are heavily physics-based, but also basically the only way to get robots to actually work. And the other end, which is deep reinforcement learning, which is very flexible, purely data-driven, and could apply to any type of system, but in practice only applies to systems mostly in simulation. And so something in between this might look like online calibration for rich sensing modalities so that you don't have to carefully quantify every physical parameter, or adaptivity in a system to friction or contact forces that are difficult to model a priori. On the side of ensuring discovery, there's a lot of work in the space of recommender systems. One obvious next step is to go from auditing systems to developing design principles with respect to this idea of reachability. But it'd also be interesting to expand behind just reachability to think about not just what an individual can see and whether they can control their kind of interactions and the models, but how that relates to strategic behavior. Does my behavior affect what somebody else is viewing? And what are the incentives at play there? Just kind of the broad vision of my work is that if we're going to integrate data-driven automation into important domains, we're going to need to ensure properties like safety, discovery, equity, well-being, et cetera, whether that's traffic networks or smart grid or smart agriculture. And there's a lot of challenges here, not just kind of I guess, first of all, in defining what the properties are. How do you define a value like this as a technical specification? And then how do you make sure that's what you want it to be? And then once you're happy with the specification, like safety, for example, ensuring them in dynamic and uncertain systems is challenging in its own right. So with that, I would like to thank everybody for your attention, and then sort of thank lots of other people. So thank my advisor, Ben, as well as, well, Ben, who, yeah, I guess, let me say, when I entered grad school, I did not know what I wanted to focus on. And Ben mostly showed me that I didn't have to focus on anything and I could still do good work, or at least work that other people think is good. Also my committee, Moritz, who really brought me into the fold on sort of thinking about decision-making on populations of people and has taught me to think carefully about that. Francesco Borelli, who taught me a lot about using kind of rigorous ideas from control to make real systems work, and I admire his work there a lot. And then Claire's not on my dissertation committee, but she was on my quals committee, and she has also been a reader on my master's thesis, always a kind of source of support and just inspiration about different ways that you can think about maintaining safety in systems. I'd also like to thank my collaborators. I'll start with Nick Motney, who was a postdoc here, but is now a professor at Penn, who was like, in some ways the classic Berkeley example of the advisor, the secondary advisor coming from a postdoc. He taught me everything I know about system level synthesis, which has literally been foundational to a lot of my work. So I really appreciate that. Also my other collaborators on kind of the data-driven controls work that I've done, Horia, Stephen, and Vicky. Lydia, Esther, and Max were very instrumental in thinking about fairness, and thinking about it with them was a lot of fun. Dan and Josh are both sort of real economists, and they've helped think about what welfare means. And on the side of recommender systems, working with Mihaela has been really important in clarifying what I'm trying to say. And Sarah Rich at Canopy was sort of my host when I was doing an internship at a place that really allowed me to think mathematically about recommender systems while getting paid internship money. And then there's lots of people who I've collaborated with that in work that didn't make it into my thesis. There's a whole bunch of folks at Caltech who I've started to think about nonlinear control with. And then there's, of course, several undergraduates and also younger graduate students, Aurelia, Deirdre, and Rohan, who made some visions of a car that could race into a reality, or kind of allowed me to think about robotic ice skating in fun ways. On the side of recommender systems, I've also done work with Wencho, Carl, and Alex, writing the best research code that I've ever written. And then lastly, my work on computational imaging never quite made it in, but with Zach and Laura, I learned how to think about optimization in the context of a broader system, and that's been a really important perspective. And then I'll briefly say that not just my collaborators and my mentors, but I've had a lot of great colleagues, friends, and family. So these guys are all the kind of organizers of GEES, and many of them are not in the computer science department or the ECS department. Some of them are, but being a part of GEES has expanded my horizons, I guess, in thinking about what type of research is possible and what type of questions are worth asking. Of course, the Modest Yachts group of people that Ben has collected is great. These are the people I remember to get pictures of in time. I'm sure that I forgot some. And then lastly, my family and friends, of course, again, just a collection of pictures for always, supporting me and making it easy to enjoy life. So thank you. Cool. Yeah, questions.
Yes, so questions in the chat are welcome. There's nothing in
Sarah has to
chat.
Yeah, I can. I'm.
So Sarah, just tell people that they can ask questions on chat.
Yes. Yes. Questions on the chat are welcome. Or if you unmute and speak, I think I will hear you. I think I see Ross has a question.
Hello, can you hear me?
Yes, I can.
Hi, Sarah. Long time, first time. First of all, great talk. So my question is, it might be about halfway through your talk. You had a slide on, I think it was the perception-based control. You had a bound that had some dimension terms in it.
Yes.
I may be misinterpreting, but I think you had a comment about, yeah, it might be this slide. Yeah, I think you had a comment about maybe this being valid in low dimensions, but I think this actually gets better in high dimensions, or at the very least doesn't get worse. I don't think
I agree it doesn't get worse, but I think that in high dimension exponentials are bad, I guess is what I was saying.
Okay, well, I'm trying to.
Yeah, if you have if you can make it better, that would be great.
I think it's if you fix t, it might be close to constant, or at the very least very bounded, according to my Wolfram plot. But yeah, that's just a comment that this might actually not be bad in high dimensions.
Cool. Yeah.
But yeah, great talk.
Hit me up on Slack. Cool. Any questions from the studio audience? Yeah.
I have a question about discovery. So based on your movie thing, I like a small set of movies being recommended to me. What am I missing?
Yeah, sounds like great. That's yeah, I will, yeah. So the question was, the point of recommender systems is to give you a small set of movies that you want to pick from. So who cares about discovery, basically? And so what I'll say is discovery is not about what will happen. So what will happen is the system can still just show you a small number. It's about what could happen if you suddenly changed your behavior, essentially. And so if you like that you get a small number of movies and you never care about exploration, I'm not going to change anything for you. But for the people who are, radically suddenly have the shift in interests or something like that, then I'm proposing something that would potentially make these systems better. Or at least allow you to measure that property of the system is really where I'm at. But yes, we're over time, so no pressure to ask more questions. But thank you everybody for coming virtually. Yeah, and thanks for all the congrats in the chat.
Doesn't look like any other raised hands.
Sarah again.
Yeah. I have to say the live applauding is much better than virtual applauding.
Oh, wait, we just do this.
No, you just do this.